All right. This is the overflow lecture for the CTNT 2020 mini course, Introduction to Sieves. In the last live lecture, we were talking about the sieve of Eratosthenes, where we go through and we remove integers that are divisible by small primes p, and we ask the question, well, let's stop at some point. We removed some number of small primes and ask, how many integers are left over? Have we actually significantly decreased the number of integers left at the end? And the goal is to improve on the trivial bound. If we start with all integers less than or equal to x, and then we remove some, we know that there's at most x integers left over. And so what we want to say is that we want to be able to remove enough primes to say that, well, the things that are left over grows strictly smaller than x. That's the goal of this process, and we were able to achieve this goal. This is the theorem that we ended with last time. We have this main term, which we talked about. Mertens' theorem tells us that this product is asymptotic to 1 over log z. And so as long as z is tending to infinity with x, this main term is sublinear. It grows strictly smaller than x, which is good. That's beating the trivial bound, just so long as our error term here is also beating the trivial bound. And so this is an error term that we improved from the exponential error 2 to the z from a more elementary argument. And we talked about some choices of z that will make this error term pretty small. In particular, on this slide, we've got the choice log z equals log x divided by a times log x, where as long as we pick a to be large enough, the error term will also end up being small, because this a is going to cause the denominator to grow. And so what we're going to do now is, for the end of this section on the sieve of Eratosthenes, we're going to talk about a generalization. We're not going to prove it. The goal here is to introduce the terminology so that when you're reading about sieves, you can see this kind of terminology and say, I know what that means. I know what role each part of this theorem is playing. So that's what we're going to start right here. We'll start with a set of integers, a. These are going to be just some big set of integers we start with that's presumably easy for us to count. The example you should think of in your mind is that we start with the set of all integers less than or equal to x, just like we're doing in the sieve of Eratosthenes originally. We take our small primes p less than z, we multiply them all together. So this is a product of all of our small primes. And then we define these sets a sub p of the integers that we're going to sieve out. The example you should have in your mind is that a sub p is a set of integers less than or equal to x, which are divisible by p. These are the integers that are removed by the original sieve of Eratosthenes. The generalization, we're going to say, rather than being a set of integers divisible by p, we'll say this is a subset of integers that belong to some number of distinct residue classes mod p. So maybe being divisible by p is not the bad behavior that we're looking to remove. Maybe we're trying to remove the integers that are congruent to 1 mod p, or the integers that are congruent to a square mod p. Some condition like that. That's going to be our generalization. We're going to expand our notion of what bad integers are that we want to remove. And so our generalization of the phi function is what we've got on this next line. It's the number of elements that are in our big set of integers minus, so set minus, removed all the bad elements, where the bad elements are unioned over small primes, p smaller than z. This is the generalization. So how do we approach this? Go to the next slide here. We're going to extend the definition of a sub p to a sub d by taking intersections of these. So a sub d, this is going to be the set of integers that are bad in more than one way. So in our example, we said an integer was bad if it was divisible by the prime p. Well, what if you have an integer that's divisible by more than one small prime p? It's bad in more than one way, and if we try to remove it, we might accidentally remove it more than once. This is something we saw in the inclusion-exclusion argument. So we're going to define a sub d as the collection of all integers that are bad in multiple different ways, depending on which primes are dividing d. And for convenience, we'll just say a sub 1 is a, That's everything. So the idea is that the sum is that the integers that are left over can be counted by this sum. You sum over all the integers in A, and then you get this function, which remember, this function is equal to 1 if this GCD is equal to 1, and it's equal to 0 otherwise. So this is back to our example idea, where we're using divisibility as our bad condition, but this still works in general. And so we've got, okay, here's this condition. We rearrange the sum, d less than or equal to x, d divides p of z, mu of d, sum of n belonging to a, d divides n of 1. So now we've switched the order of the summation so that the sum of d is on the outside. This is from our example. And the sum over n is on the inside. This is our bad set that's bad for all the primes dividing d. So this is the size of this bad set, a sub d. This is just the idea using divisibility. But in general, this formula works by inclusion-exclusion. In general, the number of elements remaining after z steps in this generalized sieve can be computed as an inclusion-exclusion of the sizes of these bad sets. So this you should think of as being like this formula that we proved in the last live lecture. Where the size of these multiply bad sets were floor functions of x over d. This idea generalizes to when our sets look a little bit different, but the inclusion-exclusion is still the same. Okay, so once we get this inclusion-exclusion, the idea is still to do the same thing. Say we have a good approximation for the size of these bad sets. So we break it apart into a main term and an error term. And then we want to evaluate, well, what's the sum of the error term along d less than or equal to x and d divides p of z? That's like a sum of smooth numbers. It's a little bit smaller than the sum of z smooth numbers, but you can bound it above by the sum over z smooth numbers. And then the main term is, again, pretty similar to the main term in our original example. It looks like mu of d times this approximation, which over here the approximation was x over d. And as long as this approximation is nice enough, then we'll get a similar answer. So that's the statement on this slide. This is big and long, so let's just highlight a few facts and what they mean. This is our approximation for the bad sets. This is like x over d floor function is equal to x over d plus big O of 1. We've generalized this a little bit. We put a capital X here, even though we're looking at integers n less than or equal to little x. It's possible for capital X to be different than little x, but generally speaking, in any situation you're going to use this, it's going to be just little x again. All right. So this is saying, okay, we're approximating the size of the bad sets. The sum of this term is going to look like your main term. The sum of this term is going to look like your error term. This statement right here is just to say that your bad sets aren't too bad compared to each other. We know the sum of log p over p for p less than z grows like log z plus big O of 1. So if all of these omega numbers were 1, this statement is true. And so all we're saying is that these omega numbers, they can't get too bad. They can't be growing too fast. Like they can't all be equal to p, or they can't all be equal to p minus 3, or something like that. They have to sort of generically be small enough that the sum is still no bigger than a multiple of log z. So what this is going to tell us is that, hey, our main term, when we sum up a bunch of main terms, that's not going to get too crazy. And our error term, when we sum up a bunch of error terms, that's not going to get too crazy. The last statement, for some y bigger than 0, the size of this bad set is equal to 0 for every d bigger than y. That's just saying we can take that sum, that inclusion-exclusion sum from the last side, and we can cut it off somewhere. We'll cut it off at y. It's just a spot where we can cut it off and say, okay, well, we don't need the whole sum. We just need a slightly shorter version of this sum. That's sort of what we did in order to improve the exponential error we got in the original argument for the sieve of Eratosthenes. We showed that we could cut the sum off at some boundary for d values. And so the result is this big long thing, which doesn't look all that different from the original result we did in the final live lecture. The main term is x times a product over small primes, where now the only difference is it's not 1 over p, it's the number of residue classes, the number of bad residue classes mod p over p. So that could change a little bit. And the error term still looks roughly the same. You've got a log z term, you've got an exponential term here, where y is the place where you cut the sum off. Here you've got this thing, which x here, that looks like the x to the 1. This is the thing we want to beat. And then you've got this extra plus y over log z, which you also kind of expect you want that to be around the size of x or smaller. This is a generalized theorem. It's mostly proved in the same way. The one difference that I will tell you about, it's not really that big of a difference, but it's the biggest one that I can come up with. Is that instead of the sum over z smooth numbers, so here it's a sum of square-free z smooth numbers, which is bounded above by the sum, by the number of all z smooth numbers that are below x. Instead of this, the summation that's going to show up in the proof will look like this. So instead of summing up 1s, you're summing up this number of bad residue classes modulo d. So this is why we needed a bit of control on how bad these bad residue classes got. That's the main difference, though. If you're interested in more details of the proof, or you're trying to work it out on your own, you get a little bit stuck, check out the textbook, An Introduction to Sieve Methods and Their Applications by Kojikaru and Murdy. All right. So now we're ready for the next section, where we're going to talk about Brunn's sieves. So Brunn's sieves, they're basically going to be set up in the same way as the sieve of Eratosthenes. We're going to have a big set of integers, and then we'll have a set of bad elements that we want to remove for each prime, and we'll say, okay, remove those bad elements for all the small primes, and ask how big is the collection that's left over. The setup is exactly the same. And so what Brunn did, Brunn came up with improved methods compared to the sieve of Eratosthenes, which gives you a similar looking picture. So here's the punchline. The size of this set, it's got the same main term, x times this product over small primes, where omega of p is the number of distinct residue classes you're allowing. But Brunn got a better error term, and some of the hypotheses are slightly relaxed. This is pretty astounding, especially in the historical context, For the most part, sieve methods weren't really touched between Eratosthenes and Brun. That's pretty crazy considering that Eratosthenes lived in ancient Greece. In many ways, Brun can be considered the father of modern sieve theory, and his great improvements over the sieve of Eratosthenes motivated a lot of people to revisit the subject. Okay, so we're going to talk about two of Brun's sieves. We're not going to prove either of them. I'm going to talk about the main ideas behind them, but the proofs are a little bit too long, even for an overflow lecture when I don't have as much of a time crunch. All right. So the first one is Brun's pure sieve. So the conditions here, they're pretty similar to the generalized conditions of the sieve of Eratosthenes. So remember, we've got this, which is an intersection of bad sets, and we can approximate it nicely. This is like, just like earlier, the approximation of the floor function. The next two conditions are both about saying that the number of distinct residue classes doesn't get too crazy as you vary over the primes. They're bounded above by some constant. And if you do the sum over that number over p, it's bounded above by a constant times log z plus another constant. This is something that we know is true if these were all 1. The sum of 1 over p for p less than z is asymptotic to log z with an error term of big O of 1. So these properties aren't surprising, just so long as the number of distinct residue classes isn't allowed to grow as p grows. The hypothesis is that's removed is that Brun didn't need to know where these sets became empty. He didn't need to say that these sets got cut off for d bigger than y, then they were all 0. That was not necessary. So that's a pretty useful thing when you have a slightly more residue classes allowed. And Brun's result, written down right here, is a little bit better. So what's better about this? We've got, this is a main term. It's the same main term as the sieve of Eratosthenes. We've got two error terms here. The first one is literally just the main term divided by some powers of log z, where eta, you can pick any positive number for eta. But if eta is positive, then this exponent is negative. It's automatically smaller. So this error term is automatically smaller than the main term. We don't really have to think about it that much. It's this other error term that's the improvement. This is the one that we want to say, well, this is better than the old error term. We notice, looking at this, that there are no x's listed here. This really just has to do with z's. Okay, so let's consider this error term before we talk about Brun's leap to get to this improvement. Let's look at this error term under our nice choice for z. So we talked about in the last live lecture, the choice log z is log x divided by a times log x. That was our nice choice for z. Let's compare that. Well, let's see what happens to this error when we plug in that choice for z. Well, before I plug it in, I'm going to say that this is the same thing as, I'm not going to write big O because it'll take up a whole bunch of space. This is, let's just erase all the big O's and write everything individually. This is the same as the exponential of eta times log z times log z. So we plug in what we know log z to be. This is the exponential of eta log x divided by a log x. And then we have log of log z. Well, log of log z, we get a log rule. The numerator gives us log x. The denominator is minus log a minus 3 logs of x. All right. So let's do some cancellation. The log x here, we can cancel that with the exponent. So this is x by the power of eta divided by a times log x over log x. That's the leading power. Then there's eta times negative log a, so minus eta log a divided by a log x, and then minus eta times 3 logs of x divided by a log x. Which, if you look at this expression, these two terms are always negative. Eta is positive, a is positive, logs of x is always positive. So this is bounded above by x to the eta over a. And this is small as long as a is chosen large enough. In fact, it's very small. It's not just a slight savings on x to the first power. If you choose a large enough, you can make this thing as small as square root x, or cube root x, or x to the 1 over 100. This second error term is incredibly small. Now that doesn't mean the error term overall is incredibly small, because we also have this piece here. Really, our error term is only going to save a few factors of log z. But the fact that this middle error term is guaranteed to be smaller than the main term, combined with the fact that this second error term with our strategic choice of z can be made really, really small, that's a huge improvement. It says that, hey, our main term is going to be the main term, and it's going to be the main term by a bit more of a long shot. Okay, so before we prove this, let's actually let's talk about consequence of this. And the consequence that Brun was able to prove was an upper bound on the number of twin primes, which is strictly smaller than the number of primes. It's a pretty good bound by comparison with the number of primes. Remember, the prime number theorem says that the number of primes is asymptotic to x over log x. So for twin primes, the denominator is bigger by a whole other factor of log x, and we only made the numerator bigger by a double log of x, which is smaller than any power of log x. Okay, so let's see how we get this in Brun's sieve. So for the proof, we let our set of bad numbers be n less than or equal to x, such that n is congruent to 0 or negative 2 mod p, i.e. p divides n or p divides n plus 2. So this way we're sieving out integers that are divisible by p, or when you add 2 to it, they're divisible by p. So if we remove all these bad sets, all that will be left are the integers n, which are prime, and n plus 2 is also prime. Okay. So what does this tell us? Well, we've got S of A, P, Z. Let's say we pick Z to be such that it's our nice choice. So we already talked about how if log Z is log x over A log x, where A is sufficiently large, then we're guaranteed that the error terms are smaller than the main term. So this is bounded above by x product of p less than z, 1 minus 2 over p. Where now we have to say 2 because we have 2 bad residue classes for every prime p. So using the exponential trick, and the fact that 1 plus x is less than or equal to e to the x. This is bounded above by the exponential of negative 2 p less than z1 over p. So that's log z. The negative 2 can be moved inside one of the logs. We get this is bounded above by x divided by log z squared. And now all we need to do is plug in our nice choice for z. And so now let's talk about the twin primes, because this set, it's not the same as the twin primes. We had this conversation with the sieve of Eratosthenes. Every time we remove this bad set, we're removing all the integers that are divisible by p, or where n plus 2 is divisible by p. That also causes us to remove the prime p itself. So the number of p less than or equal to x, such that p and p plus 2 are prime, is bounded above by, well, here's the set of elements that we did not remove in this intermediate step of the sieve. But we also have to worry about, what about the small primes that we did remove? There could be twin primes smaller than z, and those got removed too. So we'll add those back in as an upper bound and say that twin primes less than z, well, that's at most the total number of primes less than z. But the total number of primes less than z, that's certainly smaller than z. So we get this is less than this term. I'm going to drop the a because it's a constant. Pi of z is bounded above by z, and we have this formula for z. So I'll write in blue when I solve for z. Z is exponential log x over a log x, which is x. I won't write it here. The exponential and one of the logs can cancel out. This is x to the 1 over a log x. And, well, as x grows, this exponent is going to decrease with 10 to 0. So this is certainly smaller than x to the 1. It's in fact smaller than x to the 1/2. And so it's definitely smaller than this term. So this is the main term. And this is the error. So it's definitely smaller than the main term. So we've proved this theorem of Brun. Okay. Now this is pretty cool. I mean, just the fact that we have an upper bound for twin primes in and of itself is very cool. It doesn't answer the twin prime conjecture because this function still tends to infinity as x tends to infinity. So it's still possible there are infinitely many twin primes. They're just a bit sparser. But this bound is sharp enough to prove a pretty neat result, which is that the sum of the reciprocals of the twin primes is convergent. This is a little bit different than prime numbers. One of the proofs that there are infinitely many primes is that the sum of 1 over the primes diverges. So Brun was able to prove that the twin primes are so much sparser than the prime numbers that the corresponding sum is actually convergent. And the proof is, once again, it's Abel summation. So we do Abel summation, where we let a sub n be 1 if n is the lower part of a twin prime pair, 0 else. Capital A of t is the number of twin prime pairs where the lower one p is less than or equal to x. And the functions would be 1 over t and the derivative minus 1 over t squared. So we do this process. We know that all primes are bigger than 1, so I can put a bigger than 1 right there. We get a of t over t from 1 to infinity, plus the integral from 1 to infinity a of t over t squared, where it's plus because this minus sign will cancel out with the original minus in the Abel summation formula. And then we use the upper bound for the number of twin prime pairs. We know that a of t is bounded above by t times log t squared divided by log t squared. So we get that this is bounded above. I actually want to be careful. Let's make this 1.5. Just to be careful. The limit as b goes to infinity. When we plug in the upper bound right here, it cancels out with the t on the denominator. Log b squared divided by log b squared plus a constant when we plug in 1.5. Now this integral will also bound above capital A. So we'll get log t squared divided by t log t squared dt. Okay. First things first. This limit tends to 0. Log b on the denominator definitely grows faster than the log b on the numerator, and you can check this using L'Hopital's rule. Next, by doing the substitution u equals log t, this improper integral becomes the integral of log u squared divided by u squared du. The extra t on the denominator becomes part of the differential. Du is dt over t. We still got the plus big O of 1. But now this integral is a bit easier to see that it converges. This converges by comparison with integral of 1 divided by u to the 3/2. So this looks almost like 1 over u squared, but the log u is just making it a little bit bigger than that. And so if I pick a slightly smaller power for the denominator, we can compare with it and still get a convergent integral. And so what does that tell us? Well, this is a constant. This is a convergent integral. It must also be a constant. The sum over all twin primes is a constant. We did it. This is a pretty famous result credited to Brun, but Brun has used his sieving techniques to prove much more powerful results than this. Brun was, I believe, the first person to prove a result that there are infinitely many pairs of integers which are products of at most 7 primes, or some number like that. That has been improved since then. But it really shows how much of a leap Brun's ideas were from the sieve of Eratosthenes, that all of a sudden we can start tackling these big conjectures. All right. So now what we're going to do is we're going to talk about the ideas behind Brun's sieves. And we're not going to prove the entire thing, but we'll discuss some of the main ideas and why these ideas are actually giving better results. So here's the big idea for Brun's pure sieve, the truncated Mobius inversion. We had this sum over d divides n of a Mobius function show up all the time. We know that it's equal to 0 if n is not 1, and it's equal to 1 if n is equal to 1. And this was used to sort of do our inclusion-exclusion argument and eliminate special terms. Now, this lemma says that we can approximate this sum, it's like approximating 0, but we can still do it, as a sum over divisors of n that have a bounded number of prime factors, plus something that has absolute value smaller than 1, times the number of divisors that have one more number of prime factors. Okay. Cool. Why would this be helpful to us? Well, let's look at this progression of ideas that we did with the sieve of Eratosthenes. This sum, one we started with, has 2 to the z terms. This is something we decided was a bad sum. It was too big because 2 to the z is a very large error term. And so what we did to improve this is we said, okay, let's truncate this and only look at d less than or equal to x. D divides p to the z. Well, we went through using Rankin's trick and showed that the number of terms in this sum is at most this many. That's a bit better. In terms of z, z doesn't affect the growth as much, but it's really close to x. We can only get a small savings on x to the 1 with a sum of this size. But when we were talking about Brun's pure sieve, I was talking about how the second error term was a much bigger improvement on x. And that's because if we instead, rather than truncating the sum by saying we're only looking at d smaller than or equal to x, well, what if we only look at d that have less than or equal to r prime factors? Well, choosing divisors of this product of primes, that's basically saying d is a product of some number of primes less than z, but now we're saying we can only pick r of them. So if you're choosing r primes from the collection of all primes less than z, that's at most z to the r terms. That's a lot better. Once again, we're back to an error term that doesn't involve x, so we have a hope of this being really, really small. But now, this is just polynomial in z instead of exponential. This error term is a lot smaller than this one up here, and it doesn't depend on x. So depending on how we choose z, we could get much smaller than x to the 1, instead of only a little bit smaller, like this bound in the middle that we got with Rankin's trick. That's the big benefit here. It's the idea that integers with a bounded number of prime factors are pretty sparse among all integers. Okay. So what's the sort of idea behind the proof? The idea is that there is a combinatorial relationship we can take advantage of. We've got the proof of the truncated Mobius formula. So let's look at the sum of divisors of n with bounded number of prime factors. Well, 1 has no prime factors, so that certainly shows up. The primes have 1 prime factor. The Mobius function of a prime is equal to -1. We could have numbers with 2 prime factors. That's -1 squared. Plus ... plus the number of ways to pick r prime factors of n. That should be r, and that's an n. Okay. We can write this out as a sum of binomial coefficients. We've got 1. How many choices are there for -1? Well, it's the same as the number of primes dividing n. Or equivalently, it's the same as choosing 1 prime out of the total number of primes dividing n. So here's the total number of primes dividing n, and we're choosing one of them. The next sum is we're choosing 2 primes out of the total number of primes dividing n. And etc. Where now, instead of going all the way up to choosing all the primes, we stop at r. This is the sum from k equals 0 to r of the number of primes dividing n. Choose k times -1 to the k. And the punchline is that there's a very nice combinatorial relationship which tells you that this sum of binomial coefficients is equal to a different binomial coefficient with some sign. So this is an exercise. This is the lecture exercise for this section. It's really just about binomial coefficients. You can replace the nu of n with some other integer, whatever other integer you want, whatever other letter you want, and this is still true. And once you have that, we now know that this sum over divisors of n with bounded number of primes is actually equal to plus or minus a special binomial coefficient. Okay. So let's look at the original sum. We know that the original sum is either 1 or 0. And so as long as we don't pick n equals 1, that's equal to 0. And this is going to be bounded between the sum over divisors with up to an even number of prime factors and the sum over divisors with up to an odd number of prime factors. Because the even or odd is going to control the sign of these two sums via this -1 to the r right here. So then, if we subtract the far right-hand side from both sides, we get a lower bound of the sum of divisors with exactly 2r plus 1 factors. We get the difference between the sum over all divisors and the sum over a bounded number of divisors, which is bounded above by 0. And that's the proof. The sum over all divisors minus the sum over a bounded number of divisors in absolute value is no bigger than 1 times the absolute value of this sum. A similar argument works if you want to go in the opposite direction. If you want to take an odd number of divisors, or an odd number of primes, and subtract that over here, you instead of putting 2r plus 1 right here, you put 2r minus 1, and then you subtract it, and then this side, what we left over is divisors with exactly 2r primes dividing them. Okay. So there's the proof of the truncated Mobius sum. All right. Now let's actually walk through this idea for bounding the quantity in Brunn's sieve. We won't do the whole argument, but I'll show you where this becomes sort of useful for us. All right. So we're going to look at this phi function again. And I'm not going to do phi. The notes I have on my other screen say phi, but I should really say this s function. We're looking at the sum of elements in our big set A, but we don't want the elements that are not co-prime with A. Okay, so there's our Mobius sum. This is going to cause our error to be really big if we leave it like this. We break this apart as a truncated Mobius sum. So we've got bounded number of prime factors plus some theta, which is in absolute value at most 1, times the sum of divisors with exactly r plus 1 factors. like that. All right. Now let's put these together. Let's take this sum and push it into everything else. The leading term, we know this is going to be an inclusion-exclusion of the sizes of the bad sets. So this is the sum over D dividing P of Z, mu of D, size of a bad set, the set we want to remove. And now, instead of being truncated by saying D is less than or equal to X, it's now truncated by saying D has at most R prime divisors. Over here, now we're taking a sum over all D that have at most R plus 1 divisors, and then a sum over all elements of A. So this is bounded above by X, which X by itself we're calling the size of A, times the number of possible integers D that fit this picture. Well, we're looking for D which divides both of these numbers, but let's just say D only divides P of Z. So the number of D dividing P of Z with nu of D equals R plus 1. That's like choosing R plus 1 primes from pi of Z primes, pi of Z total primes. So you can write that as a choose function, pi of Z choose R plus 1, but in fact, I'm going to use a bit of an upper bound on that. This is an upper bound for pi of Z choose R plus 1. Okay. So at the last step, what do? This sum on the left, this is going to have the sum of our main terms. So when we approximate A sub D, we have that X, mu of D, omega of D divided by D with this truncated sum. We have the error term, big O, of a sum of omega D's over this truncated sum. And then we have this other term where I'm even going to be a little bit cavalier and bound the number of primes below Z by Z. So now we've moved our way down to this part where we've got this truncated main term sum, where we really want to say the main term should be without this bound on the number of prime factors, because that's what we would need to match the main term in the Sieve of Eratosthenes and Bruns-Pure sieve. And then we get these two error terms, both of which can be shown to be pretty small. All right, and so I'm not going to do the rest of the proof. I just wanted to show you where the truncated Mobius sum shows up. And so down here we can see where here's a power of Z, where we might have originally had in this sum an exponential 2 to the Z showing up. Down here is a truncated sum, which can't possibly be too big. This is also going to look like a power of Z, but involving a sum of these omega functions instead. And then here's going to be the main term, which we have to worry about making sure the truncation doesn't break too many things in the main term. And it turns out it doesn't, but this main term, taking care of the truncation here, removing that is going to be what gives us the middle error term in Bruns sieve. So I'll just tell you real quick that the optimal choice for R is the closest integer to eta times log Z. Why log Z? Well, the idea is that on average, the number of prime factors of any given integer is log Z. So we think of the number of integers less than or equal to Woot's number of prime factors is less than or equal to some multiple of log z, we think of that being a typical behavior of an integer. So that means that if you choose r to be this big, we've captured the typical behavior of an integer in our main term, and then everything else will really be error terms. This idea that the average number of prime factors of an integer is log x, it shows up in one of your homework problems in the section on prime numbers. I ask you to compute the asymptotic main term as a differentiable function for the smoothed out version of the number of distinct prime factors of an integer. If you divide that by x and take a limit as x goes to infinity, that's finding the average value of that function, which the average value you'll find is log x. All right. So that's all I'm going to say about the ideas behind the pure sieve. Brunn took this one step further. Brunn says, well, why stop there? Why look at truncating the Mobius function and bounding that in terms of the number of prime factors? Instead of doing that particular kind of truncation, you can weight the Mobius function with something else, some other function g. And so the example would be in the pure sieve, the function g would be equal to 1 if d has less than or equal to r prime factors, and equal to 0 if d has more than r prime factors. And this approximation has a pretty small error if you choose g appropriately. What Brunn was able to prove was that by strategically choosing special weight functions, he could get upper and lower bounds for the number of integers left over in an intermediate part of the sieve. And on top of that, these upper and lower bounds that he chose are easier to compute. He picked these nice functions that give you easier summations. Now, this is pretty nice. It does something that we haven't gotten so far in our sieving techniques, which is getting an explicit lower bound. That's very powerful, and that's the kind of thing that you would want to have in order to prove something like the twin prime conjecture, where you want to show that there are infinitely many twin primes. You want a lower bound for the number of twin primes. So I'm not going to walk through a whole lot of the proofs of this fact. Already the truncated Mobius function is a bit involved. This would only be more so, and I don't think it would be valuable to just walk through it on our own. I think it would be a lot more valuable for you if you walked through the proof and worked out the steps on your own. But the result that Brunn gets at the end is upper and lower bounds for the numbers left over after sieving. That looks something like this. Okay. So this result, Brunn actually sacrifices some accuracy on the main term. He gets an upper bound that's some constant times this main term plus an error, and a lower bound which is a different constant times the main term plus an error. So this better sieve, it's actually less accurate on the main term for very small values of z. But the error term is significantly better. We don't have that middle piece, which, remember, the middle piece in Brunn's pure sieve was just the main term divided by some powers of log z. Now our error term is just z to some power theta. And Brunn gives theta explicitly and is able to find theta pretty small. The textbook, An Introduction to Sieve Methods and Their Applications by Kojikaru and Murdy walk through the process of showing that you can choose theta to be less than or equal to 8 if you're trying to sieve out to twin primes. 8's not a tiny number, but it's not very big either. Which means that you can pick z not like some kind of weird log thing. We can choose z to be anything less than or equal to x to the 1 over theta. Or maybe we'll put 1 over theta minus epsilon. that will still guarantee that both of these errors are smaller than x, and we'll get a non-trivial savings. But this is a much bigger choice of z than we were able to pick before. Remember, our earlier choice of z, log z equals log x divided by a log x, where if we apply the exponential function, this is z equals x to the 1 over a log x. This is smaller than any power of x, because as x gets really, really large, this exponent is going to tend to 0, no matter what you pick for a. So this is a huge improvement on Brunn's sieve. We can choose z to be much, much, much bigger for this main theorem. And in the exercises for this section on Brunn's sieves, I give a problem that talks about why having such a huge choice for z is useful and how you can use it to conclude some facts about twin primes or twin almost prime numbers. And I guess the last thing I'll talk about is the loss of accuracy on the main term. What's happening in this loss of accuracy might not be too surprising. This x times w of z term, generally speaking, we don't expect that to be the main term when x is too big. We expect it to be the right order of magnitude, but it's off by a constant. The place you want to look for the expected main term is the Hardy-Littlewood conjecture. I guess specifically the first Hardy-Littlewood conjecture. There are some exercises talking about that conjecture in the homework, but if you dive into the literature and read a bit about what the Hardy-Littlewood conjecture predicts for the constant in front of the main term, it doesn't agree with just x times w of z. It's a little bit different. And so that's another place where it might not be too surprising that Brunn's extremely stronger result had to lose some accuracy on the main term, because we actually expect the constant out front to be different than just x times w of z. And so we had to have some, possibly a range here, so that there's room to put it in a different spot. All right. That's it for the overflow lecture. I hope you enjoyed the mini course with sieves and with a lot of analytic number theory in general. The material can get really dense really quick. And so I wouldn't find it surprising if any of you following along these lectures got to a point where you thought to yourself, wow, there are way too many logs, exponential functions, bounds, integrals, that I'm lost. That happens to me. It's happened to everybody I've spoken to when they've been learning about analytic number theory. It's a process to get used to seeing all of these complicated analytic functions. And the best way to get used to these kinds of functions, in my opinion, is to work out some of the steps on your own. Do practice problems, of course, but even to just, when you're reading a proof, actually try to reconstruct it on a scrap sheet of paper. All right, that's it for the mini course. I hope you enjoyed CTNT 2020. And I guess the very end of the video, since technically, if this is an overflow video, it will be at the end of the summer school. I should thank the organizers for putting on this summer school and for inviting me to give a talk. They did a lot to set up CTNT to still function in the time of COVID-19 and to happen online. It was very successful, in my opinion. Everything ran very smoothly. And so thank you very much to the organizers.